Good afternoon, Professor.
Good afternoon, Caroline. Well
Good
done.
afternoon, Professor.
Good afternoon. Well done. Wait, now that was, I knew, excuse me, that was Caroline, but then who, how did I miss, who was it? Who was, not that it matters, but maybe it does matter. Who was that right after Caroline? Sorry. No, you're not gonna, okay. Well, good afternoon. Good afternoon. Hold on, there's more people coming. I totally appreciate it. I know, see, if only life were like, but it can be. Okay, so good afternoon, Caroline. Good afternoon, person who just said that, who I definitely appreciate and don't want to mess. But he is like kind of bothering me. Who was? Well, okay, I guess I'll figure it. Maybe I'll figure it out in the chat. All right, and good afternoon. Here we go. Good afternoon, Kevin. Good afternoon, Alicia. Good afternoon, Jamalette. Hi, Christina. Good afternoon, Felicia. Good afternoon, David P. Good afternoon, Chloe D. Good afternoon, Samuel. Good afternoon, Shamil. Good afternoon, Adan. Cool. Okay. And we're gonna, the goal is for me to waste less and less time, not waste. The goal is for me to spend less and less time each day on things that aren't directly mathematically physics. So, all right, so we're gonna get straight. So yesterday was like a big discussion, like very, maybe it seemed very philosophical to you or very conceptual or very unmathematical. I don't know what it seemed like. We're going to be using what we got out of yesterday sort of like for the rest of our lives. It landed on three verbalized forms of Galileo's principle of relativity, and then fourth form of Galileo's principle of relativity, and that form is very mathematical, so we're going to have to get into the math of it and use the math of it eventually. But just for the moment, just to be clear, like, so hopefully you got that. Hopefully you got that the takeaway from yesterday was 4 forms of Galileo's principle of relativity, all of which are ways of understanding velocity, the ultimate real big point. Maybe even write this down if you, we did write it down, but the big takeaway of all of yesterday, especially if you thought that it was like like this, and you're looking for like, what am I supposed to be hanging my hat on from all of yesterday and all of the discussion from the week before, the thing to hang your hat on from all of that is that velocity is a relation between two objects, always in physics, always in science. Velocity is never a property of one single object. Velocity is not ever something that something has. It is always something that something has in relation to or in comparison to something else. It's a huge, in other words, one of a million ways of, and again, like that drives all of physics all the way through from the 17th century to today, to the 21st century, and anything that you've ever heard, happily or not, about Einstein and relativity or special relativity or general relativity or anything you've ever heard about time, space, weirdness, or the speed of light or the twin paradox. I'm using a mocking tone of voice, but the truth is I love all of that stuff, and I firmly believe in all of that stuff. I believe in it more deeply than I believe in almost anything. All that stuff about Einstein. So if you find it enchanting or you find it alienating or any of these modern things that sort of swirl around Einstein and space and time and the term relativity, I promise you it all, and not to mention any just basic physics that we have to do, it all actually starts with Galileo's concept of relativity. And let me even go another step to say that Einstein directly says this in his original seminal work of the electrodynamics of moving bodies, where this gets laid out, where Einstein first in 1905 writes about the special theory of relativity, or what becomes known as the special theory of relativity. He absolutely says the entire thing rests on 2 premises, 2 postulates, if you like. And the first of those 2 postulates is literally Galileo's principle of relativity, which he directly attributes to Galileo. So Galileo is is the founder of anything you've ever heard about relativity. Relativity gets weirder and weirder and more interesting, perhaps. But it all starts with Galileo trying to make sense out of whether the Earth is moving or not. And at the risk of belaboring this, let me again say, then the takeaway, you might have thought from third grade or from solar system projects or this and that, and you might have thought something like people used to think that the Earth sat still at the center of the universe and the sun went past it. And then people found out from Galileo that in fact, the sun sits still at the center and the Earth goes past it. I'm not saying you do think that, but you might think that, or you might have thought that, or you might have thought you learned that. I'm here to say that is not what Galileo said. The takeaway from Galileo is not that in fact, the sun sits still in the center and the Earth goes past it. The takeaway from Galileo is that velocity is a relation. That velocity depends on point of view, on perspective, on what we ultimately call in physics frame of reference or reference frame. That to the sun, the Earth is going past it, and to the Earth, the sun is going past it. And as long as neither one of them is accelerated, then both of them have an equal claim on the numbers and on the truth and on reality. Like, okay, velocity is a matter of perspective. It is relative. That is the takeaway from yesterday. Yeah, from literally yesterday. Okay, it'll come up again and again in conceptual and mathematical forms. It landed on the mathematical form known as form 4 that has to do with addition of velocities. Now I'm going to say, now that I've just said that again, of course, if there's any question, and there might be, and sorry, and if hello, and there more people are coming, sorry, and probably someone's telling me in the chat that someone's waiting in the waiting room. Sorry. I'll look in the chat in 1 second for whatever, but let me just say, because I'm trying to, this is a little confusing, but you know, at the heart, at the base of physics is first concepts and then the mathematical symbolism. And I want to always sort of try to keep those two things straight. Like sometimes we're talking conceptually, sometimes we're talking mathematically. Yesterday and the week before, we're all kind of conceptual. Now, at the risk of confusing you, I'm going to put those aside. We're going to set all that discussion aside for a moment. We're going to return to homework 4. We're going to turn to homework 4, which is much more kind of numerical, mathematical. It might be a relief for many of you. It might be a drag for some of you. Whatever it is, it's a slight change of pace. We're going to go back to homework 4 now to more direct equation type stuff. And we're going to get to equations I've been stalling on for days. So just again, just so you have perspective, we're going to turn to homework 4. We're going to be mathematical, quantitative today. The stuff that all we said yesterday and the day before, as huge as it is, as important as it is, as welcome as you are to ask questions about it continually, I am going to warn you, you're going to sort of set it aside for today, and we're going to get a little bit more concrete and linear. So you won't necessarily, you won't necessarily directly use that stuff in an obvious fashion today. That's just like a long warning or a long context. Okay, now I'm totally going to look in the chat. I see there's a lot of things going on in the chat. I apologize. Okay. I'm looking in the chat. Hang on. Oh, what am I repeating? Wait, sorry. Good afternoon, and good afternoon, direct chat people. Sorry. Sorry. Oh, I might have missed 5 minutes ago. Caroline asked me to repeat that. Sorry. What am I repeating? Repeat the. I'm happy to repeat it. I love when people ask me that. I'm totally going to open up a portal for that. Just literally saying, can you repeat that? I mean, you guys think it makes it sound like you're not listening, but it totally makes it sound like you're listening to me. But repeating what? I bet repeating the sorry.
It was what you said about velocity.
Oh, yeah, right. Great. Yes. And thank you. And I encourage everybody to follow Caroline's lead and actually try to get this down. I mean, I'm afraid to write it down because I'll get myself bogged down. But yes, the thing I said about velocity is always in physics a relation between two objects. Velocity is never a property of one single object. I'll say it one more time. I mean, that's huge. I'm glad Caroline's asking me to repeat that. Velocity is always a relation between two objects. It is never a property of one single object. So in short, it's always a comparison. And sorry, and tell me maybe in the chat or maybe privately or publicly, just tell me if you got it that time, if that was good. And let me say again to everybody, that's so important. It's such a fundamental idea in physics. Another way of putting it, you might say in English, is just like I'm saying, velocity is always a comparison. It's never a straight up description. It's always a comparison. And what that means, and I mean numerically, quantitatively, if you say something's going 5 miles, if I say the car is going 5 miles an hour, what you have every right and almost responsibility in physics is to say to me, the car is going 5 miles an hour relative to what? Like there always has to be a basis of comparison. And the basis of comparison is what we call the reference frame or the frame of reference. And the basis of comparison is the object that is regarding itself to be at rest, regarding itself, hypothesizing itself, assuming itself, declaring itself to be stationary. So if I say a car, and I guess that we get into this in the sheet in a second, I guess I'll turn to the sheet. But if I say a car is going 50 miles an hour, first of all, you have every right and responsibility to say, wait, relative to what? And then if I say, oh, I'm sorry, I kind of took it for granted, I kind of wasn't thinking, I meant relative to the earth, right? Which quite frankly, most of the time, if people ever do leave off the comparison, they probably are assuming earth. And maybe oftentimes, if we're assuming it enough, maybe we get used to figuring that we're assuming it. So like sometimes people are casual and leave off the comparison. If they do, the truth is you're often, if you have to assume, you'll probably assume they mean relative to earth. Although quite frankly, in physics, what you really do is if someone leaves off the comparison, actually what you're supposed to fill in for them in your mind is compared to the lab. Like if we're really doing physics and I say the ball went 5 miles an hour, what I really probably mean if I didn't finish my sentence is relative to the lab. And the lab is assumed to be fixed to earth. And earth, here's the deal, right? So, and okay, I'm getting myself, but so everything has to be compared to something. If I say that the ball or the car is going 50 miles an hour relative to earth, like what and so I would write it like V ball, like 2 subscripts, like B for ball and E for earth or something. I would write VBE equals 50 miles an hour. And if I do that, if I say the ball is going 50 miles an hour relative to earth, that means I'm treating earth as the frame of reference or as the reference frame. And it means that for the purpose of that comparison, I'm looking at the ball from the perspective of, from the center of the coordinate system of, from the reference frame of earth, which means like a video game, like it means like I'm playing like the first person video game on earth. I always get that language. I may be getting that language wrong, but like it means I'm standing on earth playing the video game, watching the ball. And it means in my perspective, I'm treating the earth as going 0. If I say the ball is going 50 miles an hour relative to the earth, it means the ball is going 50 miles an hour, like faster than earth. It means that I'm assuming I'm treating the earth as going 0 and the ball is going 50. The big point I'm making to everybody and to Caroline, and I'm sure Caroline gets this because she wouldn't have asked if otherwise, but what I'm saying to everybody is make no mistake, I'm just treating the earth as going 0 in that statement, just like you treat the earth as going 0 whenever like you walk around on earth and you don't get nauseated or like you don't get worried about it, right? We are not objectively saying that the earth objectively actually is going 0 through space or in the universe. Quite like look at the solar system model you made with fruits when you were in 3rd grade or whatever. Like one part of your brain never thinks that the earth is going 0 in the universe, and it isn't. One part of your brain knows that relative to the axis of the earth is like rotating all the time. And if you look it up, it's rotating all the time at 1,000 miles an hour. That's pretty darn fast. That's faster than the speed of sound. And another part of your brain knows, or at least believes that you know, or somehow is accepted from other science teachers, that while the earth is spinning around, it's going past the sun all the time smoothly. And if you look up this, you might think, well, it's going past the sun, but it's like, so I ignore it because it's so slow. I just like ignore it because it's so slow. It doesn't make a difference. No, look it up. If you believe that the earth is going past the sun If you look up how fast that's it, it's going 65,000 miles an hour past the sun, like always. Like if you believe that. If you believe in the solar system models that, and I'm not saying you should, by the way, part of me is actually saying you should actually think about it and like wonder about it. But if you believe the solar system models that you just casually made when you were in third grade, and like, you know, maybe you didn't, but you know what I'm talking about. According to that model, the Earth is going past the sun at 65,000 miles an hour all the time. That is faster than any airplane any of us has ever been in. That is faster than rocket ships need to go in order to escape the Earth's gravitational field and like make it to the moon or whatever. Like that's faster than what's known as rocket escape velocity, which is like 45,000 miles an hour. That's freaking fast. Like, if you believe this stuff about the Earth, you're standing on a ground that is hurtling through space at 65,000 miles an hour. And now we go one step further. Just this is the reward Caroline gets for actually asking a reasonable question. But let me go a step further. Don't even think that that's like the truth. That is not the actual truth, like that we get from Galileo. Like that's how fast the Earth is going past the sun. But if you look this up on Google now or whatever, no one in the New York Times or in NASA or anyone is going to tell you that the sun is actually sitting still in the center of the universe. It is not. It is sitting still in the center of the solar system, but solar system just means the system of things that are going around the sun. Like according to all this premise, I am at the center of the Dan Yaverbaum system, duh. Like that's the whole point. I'm the center of my system. That means relative to me, I'm going nothing. And yes, relative to itself, the sun is going nothing. Relative to its system, its frame of reference, it's going nothing. But if you look it up, you will find that the sun is going past the galactic center, the center of our Milky Way galaxy, at like 650,000 miles an hour all the time. We are hurtling through space at breakneck speeds all the time, depending on what you're comparing to. What I'm ultimately saying, sorry, I'm going to go crazy again, but it's like such a big idea and it's like so important. What I'm saying is you cannot, like when you say the car is going 50 miles an hour, you mean compared to the Earth. And then you say, how fast is the Earth going? You got to compare that to something. Somewhere for the sake of making progress, we say, okay, I'm going to use the Earth as a frame of reference. To the Earth, it's going nothing. To the Earth, the ball is going 50. That's what we always, everything is a comparison. If we want to know how fast that ball is going compared to the sun, then it's going 65,000 plus 50 miles an hour. You follow what I'm saying, right? And then finally, so to bring it all back, and then I will shut up, but again, can I point out again? This is a very big idea. Like when you're in the elevator and you're confused for a minute, oh, am I going like or not or whatever? And then you're like, oh yeah, I'm going past the fourth floor. I'm going past the fourth floor. And then if you ever are in an elevator again, and you hear a little voice inside your head, like imitating me, and you hear a little voice reminding you that Yaverbaum is saying, well, you're going past the fourth floor, but just as easily, the fourth floor is going past you. You can dismiss me if you want. You could say, all right, that's like that weird physics garbage. Like, okay, if Yaverbaum wants to think like that, like, oh, the floor is going past me while I'm standing still. Like, that's very nice, Yaverbaum, but like, come on, like really, like scientifically, like, duh, obviously, the building is still and the elevator is going past the building. I say to you, really? The building is still, so you don't believe that the Earth is moving then. So you don't actually believe what your third grade teachers taught, which maybe you shouldn't, but like, don't in one part of your brain go around believing that the Earth is moving, and then another part of your brain believe that it's ridiculous for a building that's attached to it to move. Everything is in motion. The building is not objectively sitting still and the elevator objectively going past it. There is no, there are objective realities, but when it comes to velocity, so to bring it full circle, and then I will go on, oh my God, but I am really glad Caroline asked. All I'm saying in the end, or everything I'm saying is velocity is always a relation between two objects. It is never a property of one single object. That's the nature of velocity. By the way, I'm not saying that's true about everything in life. Like I love the comparison that I think it was Samuel made yesterday to good and bad stuff. Like obviously the thing I'm saying here could be transferred to other ways of thinking or could be borrowed from other ways of thinking. But just for the record, I'm not saying all of science is chaos. I'm not saying there's no absolute truth in science, not at all. I love science because there are things that are more absolute in science. But I'm just saying velocity is not one of them. Velocity is a relation. If we want to ultimately get to things that are non-relational, that are actually just true, we have to build our way to that through physics. And it starts with recognizing that velocity is just a relation. Okay, that was babble, babble, babble. Now I'm going to look at the chat. Woo, Nelly. All right. But, if you learn nothing else but that still, as far as I'm concerned, if you really see what I'm saying, and then then the course is worth it. But okay, I'm looking at the chat. Okay, so thank you, Caroline. And maybe I haven't looked at the end of the chat. Maybe Caroline will privately tell me or publicly if I actually did. And I hope I didn't like beat an ant with a sledgehammer. Like, I hope I didn't just discourage her from ever asking the question again, because it wasn't my time. Okay. Okay. So then someone came a little later. So I think for the person who's direct chat saying they came a little late, repeating what I'm talking about, fair enough, kind of. But I think I just did, I think maybe I've been yelling so loud. And so what I'm talking about, I'm just summarizing what we got out of yesterday. To anybody who came in late, and I am going to move on in a second. I'm just summarizing what we got out of yesterday about the principle of relativity, no matter how you say it. And there's going to be, we've said it 4 different ways already. We wrote down 4 forms yesterday, 4 different ways of saying the principle of relativity. 3 of them are like in English. The last one looks mathematical. There's going to be 5 more to come by the end of the semester. There's many, and frankly, each next one that comes is yet another chapter in physics. Every next development in physics, honestly, is just another angle, a way of looking at this way of looking at velocity. Every new discovery in a way, or new topic or new chapter, is pushing this recognition further and further in our minds. So I'm just summarizing that what we got yesterday was 4 forms of the fundamental statement, and the fundamental statement in the end, so far as we can tell at this point in the course, is velocity is a comparison. It is not a straight up description. That's my summary of what we were saying yesterday. And again, that person too, direct chat, maybe they can tell me if they feel okay now with that, because so my goal to everybody, that's all a summary of what we were meant to get out of sheet number 3, which is kind of a left turn kind of sheet because it doesn't seem mathematical. But now my goal today is to get back to sheet number 4, to homework 4, and deal with more direct equation-y mathy stuff. So tell me in the chat if I'm making sense or not. Now, okay, and direct chat person who came late from Wi-Fi issues, no problem, I got you. Okay, then. Oh, great. Oh, thank you, Felicia. Oh, that's super helpful. What Felicia, so Felicia put in the chat publicly, the summary of everything I'm saying right now, or the repeat for Caroline and others. So that's totally helpful. And that totally counts as multiplayer co-op. I should say that what Caroline's doing too counts as each one of you, what you're doing. You could probably find 85 different portals to count it for participation, honestly. But thank you, Felicia. Okay, direct chat person, great. Direct chat. Okay, no problem. Direct chat people about Zoom issues, Wi-Fi issues, no problem. I answered it. Great. Oh, thank you, Caroline. That's multiplayer co-op. That's closing the loop. She could end the course right now with an A. What? I just said, okay. And so you got it now too. All right. Thank you, direct chat people. All right. It's awesome. So I'm going to move on. So I'm moving now. I'm totally wipe the slate clean for a minute, or just, don't forget everything I just said. Just set it aside, set it to the left of your mind, because now we're going to go to homework 4. I'm going to change the view on the screen. Hold on a second. Sorry. Okay, so I'm going to homework 4 here. But you can still stop me if there's any issue at any time. Okay. Oh, whoops. I think it's called average acceleration. Okay. Now first, okay, now I'm going to bear, oh, well, I'll say this. Okay, just to remind you now, because we're still at the beginning of our life together as physicists. So I'm about to finally go back to homework 4 now, okay? Oh, and homework 5 was you might have noticed in Google Classroom was rescheduled to be due not a week from yesterday, not a week from today, but a week from tomorrow. So it's due on an off day of class just to keep us going. And if you're late, you're late. It's still not a big deal at this point, so we're up to homework 4 now. I want to start making tracks through it. So I'm warning you, I'm warning right here. If you look back in your notes ever, or you're reviewing for some exam or something, what I'm about to give you is me talking and me showing you some answers, but I'm not doing the 5-step solution here. That's up to you. I'm assuming that people are getting it. For full credit, you'd have to provide diagrams and all that. I'm not doing that right now because I'd like to move forward a little bit. Okay. So stop me if there's any confusion about that. I'm just writing down notes to give answers until I don't. So in fact, well, yeah, so let me, okay, so right, so this is called average. So number 1, so the first thing, very quickly, especially on this one, because this is just a quick review for the sake. So, all right, even though I just said that, I'm going to provide a quick diagram. I'm going to say, let's say this is Berlin. So I'm looking at the problem. I wish I can't share both screens at the same time. So the problem, so please have it in front of you. We're talking about average acceleration, homework 4. Roman numeral 1 is a very quick review. It has a city of Berlin lying 700 miles north of the city of Rome, right? So here's a quick diagram. So this is supposed to be 700 miles. So here's my quick, stupid little diagram here, but here's the point of my diagram. I'm going to tell you right now, like if this is north, right, and if this is south in my diagram, I'm going to make the designation right now, which is really, like you might say, okay, that diagram, really, what's that diagram doing for us? Like, duh, I get the diagram. But the real purpose of this diagram is I'm going to put these labels in. I'm making it clear that north I'm designating as positive from here on in, and south I'm designating as negative. That's like really the purpose of this diagram, is to get that choice of coordinate system clear. Like I'm now right, because you know, this is Galileo right here. Like I'm going to get some answers to these questions, but my answers are going to totally depend on what I chose as positive and what I chose as negative. And you might make a different choice, and then you would get different answers. And both of our answers are correct relative to the coordinate system, the reference frame that we choose. Like what you know, where is 0, what is up, what is down, and so forth. So I'm choosing a reference frame in which up is labeled where north is labeled as positive and south is labeled as negative. Now and you need to know that. Like this is part of the whole relativity thing. You can't even look at my answers or learn anything from my answers unless you know they're measured relative to what. So they're going to be measured relative to this coordinate system. That's part of the purpose of the diagram. And if you have a different diagram, if you decided to make south positive, now hear me out on this. If you decided to make south positive and you decided to make north negative, you'll get different answers, and your answers are just as correct as mine. Full credit, like according to the teacher and according to physics, like academically and intellectually. But what I'm really saying from here on out, and this is why the 5-step problem solving method is important, and why Galileo, because of Galileo, is what I'm saying from here on out. You have the choice to make north whichever way you want, but you don't have a choice to not make a choice. You can't answer these questions without assigning your coordinate system, without saying how your answers are being compared, what your answers are being compared to. That's part of what we're getting from the principle of relativity. Is velocity always, like all these motion things that we're dealing with now, have to be in comparison to something. And if you leave out what they're in comparison to, then you've defied the concept of velocity. All right, I think you get my point. But so here, I'm already dwelling on it. So, but here's my coordinate system. So now I'm going to answer the questions. Let me change color because but again, these are still just going to be answers. I'm not. So, okay, total distance. Oh, sorry. All right, fine. I guess I am sort of doing the method, but the woman flies. I guess she's in an airplane. woman flies. Okay. So A, distance. So I guess you know what? I'm not labeling the steps, but I guess I am doing all the steps after all that talk. All right, total distance. Well, the distance is 700 miles. So she goes from Berlin to Rome. The total distance is 700, right? The displacement if she's literally going from Berlin to Rome, if she's going south, and if I labeled south as negative, then just to be clear, and this is the only reason this is really reviewing this is to make sure that we're now paying attention to signs and direction, all that. And this goes now not only to Caroline's question, but to someone asked yesterday, someone asked about signs. Maybe it was Caroline, actually. Sorry, somebody asked about signs yet, about direction. But anyway, it goes to that because the displacement, and stop me if this is not clear, but the displacement is negative 700 miles, right? Because she went south, and because south we designate as negative. What's the average speed for this? And again, this, stop me if this is not okay, but but this is really just to drum in the importance of coordinate system and the negatives and positives. So the average speed, if I were to do a GDP here, like average speed is distance over time, right? Triple equal sign, that's my GDP. So the average speed here this is step 4, PAW. Here I plug in the numbers. The distance is 700 miles and the time is 4 hours, right? So the average speed would be 175 miles per hour, right? I'm running out of room here, but that would be the average speed. Yes. Whoops, sorry. Stop me. And to be honest, I'm looking at the sheet right now, look at the board. So I actually can't tell if someone's in the chat. Bear with me for a second. I apologize. That's the average speed. And also, if you want me to turn back the page, it's fine too. I'm just going I'm going at my pace, but you should set the pace. So now I'm on D, where it asks, what's the average velocity? So now I'm sort of in a more technical physics. I'm in a vector quantity thing. I could start using equations, so to speak. It's asking, what is the average velocity? That's the question. Well, average velocity equals displacement over time. That's my GDP, right? So the average velocity here equals negative 700 miles over 4 hours, right? Time. And so the average, so that's my step 4. So average velocity equals negative 175 miles per hour. That's the final answer to this review. I'm going to look in the chat in a second, but again, it's just plug and chug, right? And it's not meant to be hard numbers or trick, but just notice, just notice that my final answer for velocity, for my average velocity, is a negative number. It does not mean, it's not Michael J. Fox. It's not a flux capacitor. It's not Back to the Future. Negative velocity does not mean going back in time, right? It just means going back in space. It just means that I'm going in a direction that we've designated as negative. So negative 175 is just a mathematical shorthand for saying 175 miles per hour to the south, whereas positive 175 would have meant 175 miles per hour to the north, right? Just so we want to just be clear that negatives mean something, but they don't mean something weird. They just mean direction. Okay, well, maybe you think it's weird. All right, so, right, all right. That's question 1. Now we got to get to something more interesting, but let me just look in the, sorry, I'm all over the place. I'm looking at chat. There's nothing in the chat. Okay, so we're good. All right, so in fact, I'm going to turn the page now and get to a bigger issue. Sorry, I'm going back to. Yeah, what just happened? Hold on. Speaking of flux capacitor. Oh my God. Okay. Okay. So now we get to this thing. So now we're, all right. Okay, I'm going to start. So it asks a question, it just sort of introduced this thing. It just introduced this idea of instantaneous velocity. It doesn't give us an equation yet. It doesn't even give us a method or anything, but it introduces the word. Let me give you a quick English definition of what I mean by this word, in case it's not. Let me start by saying, it sort of may be evident from the English language, but let me be clear. What we have so far in this class is a equation and a number of descriptions and observations about average velocity. We have an equation for average velocity, which is displacement per time. And remember, when we first introduced it, to be really clear, we tried to make it as clear as possible that average velocity is how far you get from one point in space to another point in space, divided by how much duration, how much time passes from one point in time to another point in time, right? It's a ratio of intervals. Average velocity is a ratio of intervals, change in position per change in moment. Then we shorthanded it. We then realized, okay, but the first instant in time for anything you're ever measuring, we sort of always call 0. Like that's whenever you're measuring anything, we always start our stopwatch like at the beginning of that interval or that phenomenon that you're measuring. So the first instant of it's always called 0. So we crossed out T naught and we just leave it as T in the denominator of that equation. But make no mistake, average velocity is an interval. I'm going to write this right now, in fact. Average velocity refers to, or requires even, an interval of space per interval of time. When I say interval, and you might want to put this in your notes, when I say interval, I mean the gap or the region or the separation between 2 points. Okay, whether I'm talking about space or time. Interval means the gap or the region or the, what was the other thing I just said? The difference, there's another word I just used. Separation between 2 points. Now, that's what average velocity is. And that's why it's an average, because it's one number that's meant to describe something that's going on throughout some interval or space or time. Lots of things might actually be going on in that space or and time interval, but the average is the one number that best describes the whole thing, that best approximates the whole thing. We now here are being asked in this, or we're being introduced now, I'm just looking, okay, we're being introduced here to the concept of velocity, not between 2 points, but at 1 point, okay? We don't have a formula for it yet. We don't have a method for it yet. But what we're assuming is that we know what we mean by it. We mean the thing that, in other words, we mean how fast are you going right now? Or how fast were you going right then? That's what we mean by instantaneous velocity. Now, we use it all the time in real life. Like you're driving down the highway, if you drive, and a cop, okay, I'm driving down the highway, and an officer of the law pulls me over and says, hey, you just passed by a school. Do you know how fast you were going at 302 when you just passed that school? Right? Totally reasonable question. And I hope that I wasn't speeding past a school. But if I turned to the officer, I would not turn to the officer and say, oh, how fast was I going when I passed the school? Well, let's see. Like I've been in my car for like 3 hours total since I began this journey this morning. And in that 3 hours, I've covered like about 60 miles total. Of course, I took 2 stops at rest stops and got gas. And then like I went really fast in the left lane for a while, but then like it turns out I made a wrong turn and I backed up for a while. But in total, I've been in my car for 3 hours. And in total, I know I've traveled 60 miles that whole time. So 60 divided by 3, well, my average velocity, officer, has been 20 miles an hour. So I was going 20 and I don't see what the problem is. I would never say that, right? I mean, I hope I would never say that. Like, that's crazy, right? And I hope you see why that would be crazy. Like, that would be a good calculation. If someone asked me, what was your average velocity over the last 3 hours? Then I would do 60 divided by 3 and get 20. But that's not what the officer of the law is asking me. He or she is asking me, how fast were you going right then at that moment when you passed the school sign? Like, not over, like, yeah, you might be on average going only 20 for 3 hours on average because you stopped twice and went backwards sometimes, like in negative velocity sometimes. So you brought your average down, but sometimes you were in the left lane going really fast. And guess what? 5 minutes ago was one of those times. Like, I'm not asking how did it all average out in the end. I'm asking you at that moment, how fast were you going? That's what is meant by instantaneous velocity. And we all believe that it exists. We believe at any given moment that you're driving, you're going at some rate at any given moment. But how do we calculate it? Like, we only have an equation right now that tells us what to get, how to get a number by dividing an interval between 2 points of space by an interval between 2 points in time. Instantaneous velocity is asking us to consider what's going on at one time, at one moment, at one point in time. And we definitely all believe that something is. If nothing can be going on at one moment, then nothing is ever going on. But yet, the separation, like at one moment of time, 0 time passes. And in one moment of time, we cover 0 distance, it would seem. So it would seem like instantaneous velocity, if we just apply this equation, we're going to get 0 over 0 every time, right? Follow, right? If we just like try to figure out how fast we're going at a moment by applying the equation, we would literally say, well, it's 0 amount of time passed in the denominator. And in that snapshot, 0 distance was covered. So we would get 0 over 0 every time. And that's crazy. Because first of all, as you know, and I'm going to say this quickly, as you know, 0 over anything is 0. But as you also know, anything over itself is always 1. And as you also know, anything over 0 is always undefined or infinity or something like that. So like we would get 3 seemingly contradictory answers every single time if we just rely on this equation. So we have to do, we have to think a little bit more deeply about how to get instantaneous velocity. It's not the same. So what I've written down here at the bottom of this page, and I'm going to turn the page now, but what I'm writing here is from now on, in fact, please like note this, from now on, I'm going to use just the letter V to mean instantaneous velocity. If V has a bar over it, that means average. But if it doesn't have a bar over it, it means at an instant. In fact, what it will often will, as you saw in the equation yesterday, often I might put an arrow over it, but the arrow means vector. It's just highlighting it's not just, it is emphasizing the fact that velocity is a vector, that it has direction, but an arrow is not the same thing as a horizontal bar. So I'm saying from here on in, instantaneous velocity is going to require its own equation or its own something. It's not the same thing as average velocity. Okay, and stop me if you don't get that. That's what I'm saying so far. It's not the same thing. It's something else. How are we going to get it? We're going to have to build to that. So it gives an example in this question. Hold on. Okay, so I'm going to say the answer. There is an equation. I mean, there is an equation as I keep sort of writing on the board the last 2 days. There is an equation and there is a mathematical way of doing it, but but ultimately the answer is calculus. I mean, okay, the instantaneous velocity is ultimately one of the reasons that calculus is needed for this level of physics. This is ultimately a calculus concept. What calculus is a means of allowing us to figure out what's going on at a point by taking into account the larger context in which that point arises or from which that point has been taken. Okay, some examples are hard, some are easier to see. We're going to start with a little less hard example to see. The example on the sheet. What I'm saying is, I'm showing, before I give you the equation, I'm showing you an example of how to get instantaneous velocity by incorporating context. So the sheet says, let me just pull up the sheet for myself. The sheet says, yeah. Okay, the sheet says a couple of things. The sheet says, I mean, again, this is homework 4. This is Roman numeral 2, instantaneous velocity. The sheet says we have this car that travels 40 miles and it takes out 30 minutes, i.e. a half hour to do that. I convert it to hours just to be consistent, but you don't have to do that, but I'm just doing it. So the car travels for a half hour and it travels 40 miles. Those are two facts that seem important that you might have written down, and they are important, and it's good if you wrote them down. But there's this other fact that is also given to us that's super important. This other fact that's given to us is that the car never changes its velocity. It's going at a constant velocity. Now, that is not always true of cars or of any objects in physics, but it can be true. And it's true if and only if we know that it's true. This car, we're told, does not change its velocity. In fact, again, the fancy word for that we learned yesterday, or one way of saying that is it's unaccelerated. It's not accelerated, or put another way, as somebody in this class asked yesterday. Somebody asked, but it's inertial, this car, right? It's unaccelerated. Now that's such an important piece of information that I want to write it down in sort of an equation-y way, in a symbolic way. I'm writing, and you see on my sheet, I wrote V equals V naught. Now, please note, I mean, you're going to see that symbolism a lot in math and science, and people often overlook it or don't know what it means when it is important. I'm not using a triple equal sign. I'm not saying that V and V naught always mean the same thing. They generally don't. V naught means how fast something is going at an initial moment, right? We learned about this 2 weeks ago. Like, something naught means the value of that something at the initial moment at time equals 0. V, from here on in, V without a bar over it means the velocity at any given point. I'm not saying, well, here, hold on a second. Just as a side note or whatever, I'm not saying that V and V naught mean the same thing. They do not mean the same thing. But I am saying that in this problem, double equal sign, they happen to have the same value. That whatever velocity this thing started with is what it always has at every single instant. We're just told that. And that's a way of writing that something is constant. A way of writing that something has constant velocity is to say its velocity at any instant is the same as its initial velocity. Okay, so I wrote that down. So now so those are the facts. The question is, I'm going to the next page. Question. At t equals, oh yeah, I probably should have left things in minutes. It was kind of stupid of me to leave it in it, but all right, but I did. So, point 3, this is kind of a weird thing to do, but point, I know this is going to confuse people, but I'm doing it anyway. Sorry. Point. Oop. No, that can't be right. It's not 0.3. It's point. Sorry, it's not. Sorry, it's. Sorry. No, yeah, that is right. Okay, sorry. Okay. So the question asks at the 18th minute, 42nd second, which I'm just converting to the 0.32 hours because for whatever dumb reason, I already converted the problem into hours. So I'm just being consistent, whatever, don't get bogged down in that. But I'm saying at this very arbitrary, weird time moment, it's asking what is the instantaneous velocity? Now it's not asking the average velocity. It's asking the instantaneous velocity. And I am telling you that right now, I want to make a big point that that's not the same thing as average. And we don't yet have an equation for it or a method for it. But I'm saying, let's look at context here. In this particular case, the context is super helpful. In this particular case, what we know, in this particular case, we know the average velocity. Well, we always know that average velocity is displacement over time. In this particular case, so that was step 3, right? Step 4, in this particular case, we know that the average velocity is 40 miles divided by 0.5. I'm just being consistent. I converted to, right? So we know in this case, the average velocity is 80 miles per hour. Now, that's what the average velocity is. Now, many of you who did this homework like 4,000 years ago, you might have then circled that number and said, that's my answer. Now I'm here to let's be very careful here. Ultimately, in like one line, I am going to tell you that, yes, if you got the answer 80, you're correct. You're not crazy. You're good. I love you. You're going to heaven, or you're going to electron heaven. But I also want to say, let's be very clear. This right here is not actually the answer yet. What I just got is the average velocity of this thing. Like it went, right. It traveled for a half hour. During that half hour, it did a total of 40 miles. So on average, for that half hour, it was going 80 miles per hour. That's all I know from that statement. But then because I know, like we don't want V average, we want V. We want the instantaneous side. But we know in this case that the instantaneous velocity at any single moment happens to be whatever it was right at the beginning. It never changes, which means that it's always one number. So this average number that I just got has to be that one number. In other words, if you took 5 exams and again, I'm being really super picky here, and I'm yelling, so I don't know why that is, but I'm being super picky, but please follow me. If you took 5 exams in this class, or in some other class, you took 5 exams, and I say, what'd you get? And you tell me, hey, my average in this other class is 80. No, is 95. And I say to you, oh, your average in that class is 95, and you took 5 tests? Like, I know what you got on the second test. Like, no, I don't, right? I mean, just because I know your average, if you took 5 tests, I don't know what you got on the second test. But if you tell me my average is a 95, and I took 5 tests, and I got the same exact score on every single test, oh, then definitely you got a 95 on every single one of those tests, because if you got anything else, then your average would be that other thing, right? So I'm saying, if we know the context, if I know that this thing always had the same speed, and I know the average speed was 80, oh, then I know in this case, thus here. So I'm saying, thus, in this case, thus, V equals the average V, which in this case equals 80. So yes, that is the answer here. I'm just trying to caution you that I had to go an extra step and say, well, since the average is 80, and since I know that the velocity was constant, then I was able to get that the instantaneous velocity was 80. In other words, the summary of what I'm saying here, and then I'm going to move on. Summary is when, well, no, I'll say, if with two F's, you might want to write this in your notes. If I write, just like triple equal sign means, you know, a special kind of equal by definition. If I ever write if, IFF, not just me, I'm not making this up, but like in math and science, if you ever write if, IFF, that means if and only if. It's a stronger, right? You follow, it's a more rigid if and only if velocity is never changing, then instantaneous velocity at any moment equals average velocity. So in that simple context, you can use your original equation, as many of you maybe did in the homework, to get your instantaneous velocity. But the real question now, okay, hopefully, and again, stop me if I'm looking at various sheets here, so I might be, no, it seems like there's nothing in the chat. Please stop me if I'm, okay, so that was like a long way of saying you probably got the answer right, but I hope you see what was really going on with your right answer, because now the real question, the difficulty becomes, what if, so now I'm like sort of off homework here. I'm just being a teacher now. What if velocity is not constant? How do we compute V? Well, the answer is we still use context. We still use context. It's just that we're going to have to look, just the context is a little harder. If velocity is not constant, we call that acceleration. Okay, when velocity changes, we call that acceleration. Let me be a little bit more clear. Acceleration means change in velocity per time. Now, remember, per time. Remember, velocity is speed and direction. So you may want to write this in your notes. I'm not, oh, cool. Oh, whoa. I could retire now. Thank you for, I don't even know what motivated Nicholas to just say that, but I'm psyched, and I'm going to open up a portal for happy moments like that. Thank you. Okay, so accelerate. So hope, stop me if this doesn't make sense, or so acceleration, really strictly speaking, means a change in velocity per time. That means change in speed and or change in direction. Because, right, so we're getting fancy now. We're starting to build something a little bit fancy here now. We're a little bit like, maybe, hopefully still makes sense. And by the way, I don't even know if Nicholas, well, I'm not going to try to read his mind. I don't know. Sorry. I don't know what, like, but maybe he even said that because it almost doesn't make sense. I don't know. But like, here's something that might surprise some of you. Velocity means speed and direction. So if you change either your speed or your direction or both, in physics, we call that an acceleration. If you speed up or slow down or turn, that is an acceleration in physics. Mathematically, I'm going to say then, in other words, mathematically. So I'm a little bit off the page now. I mean, I'm like I'm just discussing stuff in homework now, but as I guess it says in homework, from here on in, just like average velocity was defined to be change in position per time, right? Average velocity is how you change where your point in space to another point in space as the clock evolves from one point in time to another point in time. Just like average velocity was that interval over that interval. Similarly, here's a new equation. This is our new equation now. Average acceleration equals change in instantaneous velocity over time. It is meant to be it's not the same. It's not the same equation. It's not the same concept, but it definitely is a direct analogy. It definitely is supposed to be, you know, a parallel. So average velocity is change in position per time. Average acceleration is change in instantaneous velocity per time. Notice the left-hand side has bars over it, over whatever on the left-hand side, and the right-hand side does not have bars. That is not a coincidence, and it is certainly not a typo. Like, we're talking about changes from point to point over intervals, but so I still haven't even told you, right? So ultimately, let's say you're trying to figure out how fast something's going at a point, but it wasn't maintaining constant velocity. Say you want to know how fast something's going here, but it was going something slower earlier over there. Then what do? Well, as long as you know the rate at which it was gaining speed or losing speed or whatever, then you can figure it out. You're using context, you're just using a slightly deeper context. In other words, I'm saying from now on, if I wanted to know, sorry. So, okay, I see the time. We have 13 minutes. This is actually good. I think we're making progress here. He says to himself as though anybody was questioning. Oh, wait, chat. Oh, no, that was Nicholas, I think. Sorry. Yeah, that was Nicholas. Okay, thank you, Nicholas. Oh, okay. So remember what we were saying was instantaneous velocity is what's happening at a point. Ultimately, the way to get what's going on at a point is somehow to look at the larger context of everything that's containing that point. Simplest context you can imagine is if nothing was changing from point to point. If all the points are the same, all have the same velocity, then the point velocity that you're looking for is whatever the average is for the whole thing. That's the simplest. The next level is, say things are changing, but say they're changing at a rate that you know. For example, say something is gaining 10 miles per hour of speed every hour. Say a car, right? I mean, I'm sort of off the sheet now, about to go back to the sheet, but just so you see why. So we're sort of like, so you see what's going on in the sheet. Like if a car is not always going 40 miles an hour, but it's going 40 miles an hour now, and then an hour later it's going 80 miles an hour, and then an hour later it's going 120 miles an hour, and then an hour later it's going 160 miles an hour. If it's a pattern, right? If it's a pattern, we would call that pattern acceleration. The rate of how much it's gaining or losing per unit of time, we call the acceleration. And if we knew that rate, we could use that to figure out how fast the thing is going right now. In other words, if we knew that, if there was a constant rate, oh, and I'm totally going to look in the chat in 1 second, but I'm saying one way you could get acceleration, one way you could get instantaneous velocity right now would just be to rearrange this equation up here, right? If acceleration is just, by definition, if average acceleration is just the rate at which something changes velocity, then all you got to know is its original velocity and add to that its rate per time times the time, right? So that's a second way to get instantaneous velocity. It's still the same larger context of context, but it's if the context is one step more complicated, right? So example of that would just be like if you knew that it started from rest and every hour it gained 40 miles per hour of velocity, then after 3 hours, it would have a velocity of 120 miles per hour. That's what that says. So by the way, if I get cut off or I forget, that's your second equation in this class now, I think. I don't think you have any. Yeah, that's an official equation. We now have 2 official equations. Average velocity equals change in position per time, i.e. displacement per time, and average acceleration equals change in instantaneous velocity per time. Now, what is, I'm just looking at the chat. Something happened in the chat. Okay. Oh, yeah. Direct top, no problem. Thank you for joining. And thank you for telling me, and no problem. I totally understand. Just like, I'll upload the notes and please watch the YouTube video. But yes, I got you. And thank you for saying so, and no problem. Okay. kind of turns into a thick class today, sort of. So you definitely do want to get the note. Anyway, okay, but thank you. So I'm also, to be clear, we have 9 minutes left. I am sort of doing two things at once. You remember at the beginning of today, there was two equations on the board. I am sort of explaining them. I am getting to them both today. And one of them has been on the board for like 3 weeks. So we're finally putting it, we're finally getting to it. But I'm sort of in this whole sheet is sort of forcing us to look at two concepts at the same time. The sheet, the homework sheet that we're on now, homework 4, is called average acceleration. And acceleration does mean change in velocity per time. So again, yes, here's the equation for this that the sheet is really ultimately all about, right? And that is what we have finally now gotten up to. Velocity is change in position. Acceleration is change in that, is change in velocity. But I want you to notice the reason I'm sort of talking two equations at once here, or two concepts at once, is that it's one thing to say average acceleration is change in velocity per time. But if you really look at what I'm saying, you notice it's change in velocity per time. It's not change in average velocity per time. It requires us to believe in this other thing that we had never really established yet in the course. Like, we know about average velocity, but now what it's for us to understand changes, to understand acceleration, we have to be able to picture velocity at a moment, right? So for some of you, I don't know which concept should come first in your minds. They kind of run around the mulberry bush together. But I'm saying one equation that I've just now established, and now you're like responsible for or whatever, is that average acceleration equals change in instantaneous velocity per time. We use it for the rest of that sheet, homework 4. We'll continue talking about homework 4 on Monday, and we will finish going over homework 4 on Monday, rest assured. And then we'll get to homework 5, which isn't even due till, anyway, you get the point. Or we don't have class. You know what I'm saying. But please understand that the right side of this new equation, the right side has these V's in it, and those V's have never been defined in an equation for us yet. Only V bar has. So what really is V without a bar over it? Like, what really is V? V, not V bar, V, instantaneous V for all contexts and all times. Like, I'm saying the way we get it ultimately is always from some kind of context. But what I mean, different contexts are different. So what is the universal truth of V? What V is this. Sorry. And this is where the calculus comes in. These are different ways of writing the same thing. Whichever one of these, if any of these ways clicks for you, good. They all mean the same thing. Here's what I'm ultimately saying, and this will land. We have 5 minutes left. I mean, we are at the end of something. I know I have to go back and still solve the problems in the sheet. I will on Monday, but here's what I'm saying. I'm ultimately saying, oh, hold on one second. Sorry. Here's what I'm ultimately saying. And I'm going to work backwards here. What I'm ultimately saying is instantaneous velocity is the derivative of position with respect to time. I'm ultimately saying here's how things link to calculus. If you have any comfort at all with calculus, then what I'm saying is yes, if you were to make a graph of position with respect to time, if position were the dependent variable and time were the independent variable, if position were some function of time, I'm saying the derivative of that graph, the instantaneous rate of change, the slope of the tangent lines to that graph is what we mean by instantaneous velocity. If position is marked with an X and time is marked with a T, then V triple equal sign dx over dt. If you have any comfort with calculus at all, and frankly, if you do have comfort with the calculus, you may have heard this before, and good. If you have comfort with calculus, what I'm saying is what instantaneous velocity is the first derivative of position with respect to time. Now, you may not have comfort with calculus. I'm very aware of that. I know you're all required to take it. I know that. But I also know that just because you took it or are taking it, or even if you got an A, that doesn't mean that you like it. It doesn't mean that you mastered it. It doesn't mean that you feel comfortable with it. It might mean that you know, first of all, it doesn't even mean that you know how to do it. But even those of you who do it well, that still doesn't mean, oh, good, fine. No, I hope, look, I'm thrilled with the feedback that, I love this feedback that Nicholas is giving, not just because it's not just because it's positive, even if you were giving negative feedback, like it's really helpful to get this feedback. And like when Caroline asked to repeat before, this is great. And look, I hope, certainly my job is slightly easier, or your job is slightly easier. If you're with Nicholas and you feel like derivatives you can handle, you're okay with derivatives, and this is like not throwing you, fantastic, seriously. However, with 2 minutes left, 2.5 minutes left, let me also say, I don't have illusions that that applies to everybody in the room. I am not actually, I'm here to assume that you've seen some calculus before, that the ice has been broken on some calculus before, but I'm not really here actually to rely on the assumption that you're all calculus masters. I've been doing this way too long to think that. Also, I have way too big of an ego or I shouldn't say that. I mean, that probably is true, but I have too much of a personal love for calculus to not want to be part of your experience in getting to know it and love it. Like, in other words, I consider it part of my job to try to get you to see calculus through the vehicle of physics. That's actually how it worked for me. What I'm saying is, those of you in the room, again, with only 2 minutes left, those of you who don't think you like calculus or don't get calculus or don't know what I mean by a derivative, right now, first of all, it's okay. Don't give up or go run screaming. Like, I see you. But second of all, my first hint or my first like welcome to the world of calculus thing is flip what I'm saying in your mind. Instead of you saying to yourself, oh, I guess I have to now understand what instantaneous velocity is by understanding calculus. No, flip it and start trying to understand what derivatives are, or start trying to understand calculus by picturing physics. What I'm saying, with 1 minute left, I'm going to say this more extensively on the next time we have class, is velocity, instantaneous velocity is the limit as average velocity is, instantaneous velocity is the limit as we examine average velocity for smaller and smaller and smaller time intervals. Imagine the 2 points of time between which we're measuring an average to be getting closer and closer and closer together until the point where they're so close together, they're practically 1 point, but not quite 1 point. What do I mean by that? I mean something scientific. I mean, and I know it's 1:30, so I'm going to finish the sentence. We'll keep, but I'm just saying, imagine 2 points in time that are so close together that you can't measure how far apart they are. They're below the threshold of measurement, yet you can tell that there is an interval of time because something actually happened. So 2 points in time that are far enough away for something to move, but close enough together that we don't have a meter, that we don't have a clock accurate enough to measure it. Okay, instantaneous velocity is the velocity measured over that small of an interval. It's the rate of change of position during an amount of time that's so small, it practically seems like it's just one moment in time. A derivative is a rate of change taken down to such a small interval that you can't even measure the size of the interval, yet you know that some change occurred. I know it's 1:30, so I'm going to stop right there. But basically, I'm saying a derivative is a slope in a is a rate of change in a tiny interval. Instantaneous velocity is average velocity over a tiny interval of time. We'll stop right there, but thank you for the feedback, and thank you for the questions, and have a good long weekend, and I'll see you when I see you. We'll all catch up, and I'm done. Thank you. Yes, have a great day.
Have a good day, Professor.
Thank you.
Oh, thank you. Awesome. You guys too. Oh, awesome. Okay, and I'm still here if anybody needs any questions. I'm just turning off the recording and I'm changing. But thank you, Nicholas. That's awesome. Thank you all. Realsies. Okay, wait, what am I doing? I'm changing the. Oh, you're all gone. Okay. Well, bye.